function decomposition. And then we'll look at another example. Function decomposition. We're going backwards if you want. So I'm going to create this function 1 divided by x squared minus 3. I would like you to give me an inner function and an outer. To illustrate that basically 1 over x squared minus 3 is obtained using at least, there is more than one correct answer here, at least two functions. When we create the function composition, we will determine this. Of course, because when I evaluate the function, I have to perform this first. And when I'm done and I get one number, I apply 1 over x to that number. And that is the function composition. This is to illustrate any function is really a function composition. And now I would like to look at one problem with two graphs. Here we are given two graphs, let's say 92. And this is on page 311. We're asked to find in 92 f comp g of 1. We're not given f, we're not given g, but we are given their graphs. So we're going to look at those graphs and identify what we need. But before we do that, I would like to simplify this, or I would like to write what it means. So what does f comp g of 1 mean? It means, awesome, I have to start with the inner function, like always. So then what do I have to identify first? Perfect. So let's look at the graph. G is in red. I have to identify g of 1. Exactly. G of 1 is indeed -5. Awesome. Well done. So this is -5. So therefore, what is my final step? What do I need to determine now? Perfect. So now let's look at the blue graph and identify f of -5. Exactly, f of -5 is 3. Perfect. That's how we determine function composition from graphs. The value, no, I cannot determine f comp g of x, but I can evaluate by reading from the graph. Any questions? Any questions? I know I only have 7 minutes left, so I'd like to start the next section just to give you the idea. And that is 2.7, inverse functions. Inverse functions. We looked at function composition, f comp g, and we also looked at function composition, g comp f. Can you give me two functions in which one will undo the effect of the first one? In other words, let me give you a silly example. I give you $10, so you're adding 10 to your pocket, but then I come back and take it away from you. What's the deal? What did we do? The answer is nothing. Nothing, because the adding process was undone by the subtracting process. So your pocket did not change, right? Because the adding was canceled by the subtracting. Now I can do the opposite. I can take $10 away from you and then come back and give it back. So I can apply the subtraction first and then adding. What happened? Nothing. Can you give me two functions? One that is f and one that is g, that you will know that if we apply them in any order, nothing will happen to x. So multiplication by 2. So you have $10 in your pocket. We multiply them by 2. So you have 20. But in order for undo that, what will I have to do to your 20? Not subtract. So what multiplication and subtraction are not opposite operations. I have to divide, correct? So if I multiply $10 by 2, I have to divide the answer by 2 to annul the first process. Perfect. That's a perfect example. So let's say f of x equals twice x and g of x equals 1/2 x. These two operations are inverses of each other, correct? Adding 10 and subtracting 10, opposite operations. Multiplying by 2, dividing by 2, opposite operations. Square root and inverse operations, right? So if we want to create the function composition, either f comp g with these two, or g comp f, what will the result be? You could say, wait a minute, let me calculate. But we already know the answer. What is the answer?
0.
Not 0. Whatever I had initially, x. So if this is the important property here, if the function composition of any two functions in any direction, apply the inner first and then the outer, or apply the outer and then the inner, if it happens that both equal x, f and g must be inverses of each other. And this is the only way. So this is called the property of inverse functions. The property of inverse functions. So if I'm given two functions and I create a function composition and I get x, then I know they must be inverses of each other. So let's look at one example. And that is on page 321. Let's say 7. And then we'll stop. We are given f of x equals 3 over x minus 4. And we are given g of x, which is 3 over x plus 4. In this problem, we are asked, are these inverses of each other? Show. What do I have to show? What do I have to calculate? Exactly. I have to calculate f of g of x, and if the answer is nothing else but plain x, what do I conclude about f and g? They must be inverses of each other. If I get x squared, or x over 5, or x cubed, what will I say about f and g? They're not inverses of each other. They did not undo the process of the inner. Okay, perfect. So let's determine f comp g. If f comp g is x, g comp f will be x as well. So by definition, this is f of g of x. I have to start with the inner function. I have to replace the inner function by, can anyone dictate? 3 over x plus 4, very good. Now I have to be very careful, because the next step is I look at f. Let's understand what f is saying to us. F says 3 over whatever minus 4. 3 over whatever. What do I mean by whatever? What do I have to write? Minus 4. 3 over whatever minus 4. Awesome. What happens in the denominator? Yes. And now remember, the numerator is a fraction. What fraction? 3 over 1. What is the denominator? 3 over x. How do I divide two fractions? I copy the fraction from the top, and I do what with the fraction from the bottom? And I get x divided by 3. If this answer is x and plain x, not x plus 1, not x over 3, nothing else but plain x, and it is, what do I conclude? Yes, inverses of each other. I checked. F comma g is x. G comma f will be x as